Well, hi there, everybody. Welcome back and happy senior year. I'm really excited for you guys to try this new experiment of having a BC class be sort of an independent study. But as we work on it, you work on it independently. I don't want you to feel alone. I want you to feel supported by me, but also by your other classmates that are doing this together. So please reach out, do this with a group. I hope you guys get a group text going where everybody's collaborating together. Don't hesitate to ask questions of each other, ask questions of me as we work through this first semester in this unique way. All right, so the idea is that you will be watching videos and taking the notes ahead of time. That, for the most part, that will be your homework. And then I want you to come to school, and I'd like you to do the homework with the people who are in your study hall or your small group. That would be the ideal way to do it. Okay, that's the way I'm envisioning how this is going to go. But since this is our first one, you'll be watching this video in class. All right, so what we're going to do is going to go back. We're skipping chapter 0. We're going to jump right into chapter 1, which should be a review chapter with a few new things sprinkled in, just to lay the foundation. We're going to go real fast through chapter 1. In fact, we're going to have a test already on it next week. This is just reviewing what we learned last year about limits and how that's really important for the development of calculus to have a good understanding of limits. So we'll talk about how you evaluate limits, what you can and can't do with them, and proper ways to write them. And the new thing we're going to learn today is the squeeze theorem. We didn't really talk very much about that last year. So let's define a limit. When we read limit, we say the limit of f of x as x approaches the value c equals, and then that's denoted as capital L. The notation is what we're going to be focusing on, okay, using good limits, using good equal signs, making sure we write limit as proper notation, okay? When we look at a limit, sometimes we get confused with the idea of continuity versus a limit. You're looking at 3 different graphs here. They are in various stages of continuity, but that's not what we're talking about today. We are talking about a limit. And so a limit is defined as a value approaching from 2 sides, okay? Approaching from side A, and we approach that from the left, and then we say of f of x. And we compare that, so it's like versus, sort of, those 2 things. The limit as x approaches from the right of that same value of f of x. And what we're doing is we're comparing those 2. And if those 2 things are equal, then we can say that these limits are equal to each other, and we call that value L. And so on the graph, in this first example, the left limit approaching 1 from the left and approaching 1 from the right are both approaching the same number. And so we say that value is L and that value exists. In the second example, approaching from the left and approaching from the right also approach the same value, and that value is L. Now, there's a distractor value down here. Okay, that is the value of f of 1, which is not the value of L. And so that's irrelevant to the fact whether or not this limit exists or not. The limit still exists and the limit is L. And in the last one, that's the most obvious one, where the left and the right limit do approach the same value, and that value is L. So that's clearly a limit as well. So all 3 of these, the limit does exist. When you're working with limits, there's things you can and can't do. You are allowed to add limits. That's one of the things you can do. You are allowed to subtract limits. That's another thing that you can do. You're allowed to multiply 2 limits. You're allowed to pull a constant k out in front of a limit. And so that's why we have k sitting here in front. That's legal. You are allowed the quotient rule, as long as what you're working with in the denominator is not equal to 0. So we will get to that when we have those situations where what do we do when we have 0 at the bottom? And what do we do when we have both 0 in the top and bottom, that indeterminate form? That will come up again later, but let's focus on what we can do today. So when you're evaluating limits, one of the easiest ways to evaluate a limit is to do it algebraically, where you simply substitute the value in for x in each of the situations. So we use good equal sign notation. Once you have substituted the value, you do not need to write limit anymore, but as long as there's variables, you still should be writing limit. But I'm not going to have any variables anymore. I'm going to go ahead and drop the 5 in. And so then we'll be evaluating this. So that'll be 4 times 25 minus 10 plus 6. So we're looking at 100 minus 10 plus 6. So we're looking at 96 is the value of that limit. And that would mean from both the left and the right-hand side, the value is going to be 96. For the second example, when we try plugging 0 into the variable, so we don't need limit anymore. So 1 plus the sine of 0 over the cosine of 0. So notice my good use of equal signs, also my good use of parentheses. But my parentheses are getting put around the value that I'm substituting in. The sine of 0 is 1. The sine of 0, let's do a little summer brain there. The sine of 0 is 0. The cosine of 0 is 1. So we end up with 1 over 1. So the limit value is 1, which means the left and the right-hand limit both approach 1. All right, we'll try direct substitution again in this situation. So I'm going to take the value of 0, substitute it in for all the values of x. So that's going to give me 2 squared minus 4. It's also going to give me 2 parentheses cubed minus 2 parentheses 2 squared minus 9 times 2 plus 18. So my numerator, I'm going to have 4 minus 4, which isn't a problem. My denominator, I'm going to have 8 minus 18 plus 18. Now I end up with a problem, which is 0 on the top and 0 on the bottom, which is an indeterminate form. That means I need to start back over again. So I'm going to go back and reset this problem. I'm going to change colors just because I am doing a reset, and I got to try something different. Right now, the different thing I'm going to try is factoring. This would factor into x minus 2 and x plus 2 for the numerator. That's the difference of squares. The denominator, let's take a look at that. Let's clean this up a little bit so I can take a better look at it. I'm going to do what we call group factoring. So I'm going to factor the first 2 terms, take out x squared, and that leaves me with x minus 2. And then I'm going to factor the second 2 terms. I'm going to take out a negative 9. That also leaves me with x minus 2. So that kind of factoring where you factor by groups allows you to keep factoring. So my numerator is x minus 2, x plus 2. My denominator now, this is algebra, where I notice that both terms have x minus 2. So I recognize that x minus 2 is a common factor. And then x squared minus 9, the remainder parts, this term that's left here, I could write x squared minus 9 as the second factor, but I also know that that is the difference of squares also. So instead I'm going to say x minus 3, x plus 3. And what I recognize right now is that in the numerator and denominator, the same factor of x minus 2 is present. So that factor can be reduced. So I'm using division to simplify. Notice that because I still have variables, because I still have x's, I am keeping my good notation of using the limit, writing the limit, and using good parentheses. All right, now we can directly substitute the 2 back in. So I'll take this value of 2 and I'll substitute it in for all my x's. That's going to give me 2 plus 2 in the numerator. It'll give me 2 minus 3 and 2 plus 3. So it'll be 4 over negative 1 times 5. So we're looking at negative 4/5. So negative 4/5 is the value of this limit from both the left and the right. Just in case you're wondering, I know that the 0 over 0 is something we called an indeterminate form. And later, we learned that you could use derivatives to solve an indeterminate form with the rule called L'Hopital's rule. But technically, you don't know anything about derivatives yet, and you don't know L'Hopital's rule yet. So the only way to tackle this is with factoring. All right, so we have algebra where you could just drop numbers in. We have factoring as a technique. Another technique we can use is the technique of graphing, and we look at one-sided limits. So when we talk about that, we use words like the right-hand limit or the left-hand limit, and we use this notation, which you've already seen me do. That should be familiar to you from last year. And what that allows you to do is find limits visually, looking at a graph and being able to tell what's happening. So if we're looking to find the limit approaching 0 of this particular hyperbola, we look at what's happening as x is approaching from the left-hand side of 0. And so this is approaching in a negative sense. So we have the limit as x approaches from the left of 5 over x. And that's going to be negative infinity because it's heading down along that asymptote. And then when we look at the value from the right, we can see that that's increasing towards positive infinity. And because those two values are different from each other, we can conclude that the limit does not exist. All right, now that we could probably get a pretty good idea. It suggests it from the picture. You can look at the picture and be like, oh yeah, duh. Of course, the limit does not exist because there's an asymptote here along this x-axis, a y-axis, excuse me. But algebraically, this is how you would show it, okay? You would show that that does not exist. So the limit approaching straight out 0 does not exist. DNE you can do because negative infinity isn't equal to positive infinity. Those are two different things. The left-hand limit and the right-hand limit are not the same. In order for a limit to exist, the two sides must be equal. The left and the right must have the same value. Then you can conclude that the limit, it does exist. I love this symbol that they use right here. Okay, that means both. Both statements must be true. This statement must be true and that statement must be true. They all must equal this value here of L. If that's true, then we can conclude that the limit overall must be true. Okay. All right, so let's look at the graph again about the different sided limits. Okay, so we want to approach 0 from the right. So looking at approaching 0 from the right, that means we're coming along this graph and approaching 0 from the right-hand side of the graph. And so that value as we approach is 0. Approaching 2 from the right. Okay, approaching 2 from the right. Boy, there is nothing on the other side of 2. There's a big gap between 2 and 3. If you zoom in on that, like between these two spaces here, there's no graph at all. There's no function. And so that limit does not exist on the right-hand side. Approaching 2 from the left, now we're approaching, going up along that positive slope, and that is approaching the value of 4. So then if you compare those two, the limit from the right and the limit from the left, they are not equal. So we would conclude that the limit approaching 2 does not exist either. And the limit approaching 3 from the right, here's 3 and approaching from the right-hand side, and we assume that this is a closed value right here, and so that would be approaching 0. So those are different ways you can read the graph to find the limits, different one-sided limits. All right, this is the last thing we're going to do, and this is the new part. We're going to talk about introducing the squeeze theorem as an official theorem that you'll need to know and be responsible for. The idea of a squeeze theorem takes 3 comparable functions. So we're talking about relating function f to 2 other functions, function g and function h. And we call it a squeeze. Some people call it a sandwich because there has to be a high function, a middle function, and a lower function. So in this case, we would say that the lowest function is the function g. So we say g of x. And that's lower than. And then the higher function we usually claim is h of x, and that one's always the biggest function. And then f of x is right in between. So this sort of a sandwich idea, okay, that you've got 2 pieces of bread with something in the middle, or we're going to squeeze all of these things together. The way we squeeze them is by introducing the idea of a limit. And so we say, okay, well, what if we take the limit of all 3? The limit of the g function on the bottom. And we take the limit of the h function on the top. What can that tell us about the limit of the f function in the center that's squeezed in the middle? And if we can determine something about the larger limit, and if we can determine something about the smaller limit, that might help us figure out something about the limit that has to be between them. Okay, so let's see what we can do with a function like this. Okay, we're going to use the squeeze theorem to show that the limit turns out to be 0. So what we're going to do is we're going to start with a function that we know. We know the sine of x. And hopefully you can picture that function, the sine of x, in your head. What is always going to be something that the most simple function that will always be higher than the sine of x? And so what I would think about is just the horizontal line of 1. It will always be higher or equal to, if I drew my graph correctly, okay, the value of 1 will always be at least bigger or equal to the sine of x. Similarly, the value of negative 1 will always be on the low end. And so I can say that the sine of x is squeezed between, or sandwiched between, negative 1 and 1. Okay, but I want to think about the denominator here. I need the sine of x over x. So algebraically, if I take that and divide it by x, well then legal math says if you do it to the middle, you have to do it to the left side and the right side also. And so I would have negative 1 over x, divide that, and positive 1 divided by x. So all the terms get divided by x. Okay, well, now I want to be thinking about the limit of all of these things. So let me bring that into the equation. So if I'm going to think about, well, I want to know the limit of the sine of x over x, which means if I add it to the middle, I also have to add it to the left and the right sides. So I'm going to have the limit as x approaches negative infinity of negative 1 over x, and then I'll also have the limit, oops, not negative infinity, just infinity, sorry, and then the limit as x approaches infinity of positive 1 over x. Okay, so let's plug in infinity and see what happens. So I get negative 1 over infinity. And hopefully you remember from last year, when you divide -1 by a super, super big number like infinity, you're going to get a super, super small number, and the number is going to be 0. But we're going to be on the negative side of 0. And so the answer to -1 over infinity is 0 minus. And then on the front top end, when we plug 1 over infinity there, okay, we're dividing by 1 divided by infinity, which is going to give me 0, but it's going to give me 0 on the positive side. And then I have what I'm looking for in the center. And now we've effectively squeezed this problem. The limit that I'm looking for, the limit must be greater than 0 minus and less than 0 plus. So there's only one number that is squeezed between 0 minus and 0 plus. And the only possibility then is that the limit as x approaches infinity of sine of x over x must be equal to 0. It's the only possibility because that's the only number between 0 minus and 0 plus. That's an example of the squeeze theorem. Let's look at it again. Okay, here's another example of the squeeze theorem. This is the graph in blue right here. So you can see this graph comes down and it bounces and oscillates, but is being squeezed between two functions you should recognize. The red function on the top here and the red function on the bottom. Those are two parabolas. And so we start this by saying that x squared times the sine of 1 over x is being squeezed between a negative parabola and a positive parabola. Okay, it is being squeezed between those two things. But we want to investigate the limit. And so we say, okay, what's the limit then? So then we add, well then what is the limit as x approaches 0 of negative x squared? And then compare that to the limit as x approaches 0 of x squared times sine of 1 over x. And then compare that to the limit, let me see if I can fit this in, as x approaches 0 of positive x squared. Okay, so then we know that the limit as x approaches 0, if we plug that in, that would be negative 0 squared. And then we have our central limit that we are working with. And then we have positive 0 squared. So 0 squared is still 0, but the negative side of it means we're on 0 minus. And then the other side, 0 squared is 0, of course, but we're on the positive side of that. So 0 plus. So therefore, there is no other conclusion other than to conclude that the limit of x squared times the sine of 1 over x must be sandwiched between and must be equal to 0. It's kind of like doing a proof in geometry, only you don't give the reasons, but you're following a logical process. Each step logically proceeds from the one before.